Right now, a clock on the International Space Station ticks slower than yours. Not because it is broken, because the astronauts aboard are moving at 17,500 miles per hour, and the universe itself is bending time around them. The effect is tiny, a few milliseconds over months, but it is measured, confirmed, and real. Now imagine accelerating far beyond that. At 99% of light speed, 1 year for you becomes 7 years for everyone you left behind. At 99.999%, that ratio explodes to over 200. Your body compresses, your mass skyrockets, and the energy required to push you even 1 mile per hour faster approaches infinity itself. This is not science fiction. This is what Einstein's equations guarantee. If you enjoy journeys that make the universe feel stranger than any fiction ever could, do me a favor, hit that like button and subscribe. Now, get yourself comfortable. Let's begin. There is a number buried in the foundation of everything that exists. It does not care about your opinion. It does not bend under political pressure. It does not shift with temperature, altitude, latitude, or the mood of the person measuring it. That number is 299,792,458 meters per second, the speed of light in a vacuum. Scientists have tested this value with instruments so precise they can detect a change smaller than the width of a single atom. The number never moves. It has not moved since the first photon burst into existence 13.8 billion years ago, and it will not move when the last star in the universe burns to ash. Every law of physics you have ever encountered bows to this number. Gravity answers to it, electromagnetism obeys it. The nuclear forces that hold atoms together and rip them apart operate under its jurisdiction. It is not merely fast. It is the universe's only absolute, the one constant that every observer, in every corner of existence, no matter how fast they are moving or where they are standing, will always agree on. And that agreement is precisely what makes it so dangerous to approach. For most of human history, people assumed light travelled instantaneously. You strike a match and the room fills with illumination. There is no perceptible delay. The ancient Greeks debated the question without resolution. Aristotle believed light required no travel time whatsoever. It simply appeared everywhere the moment its source ignited. This seemed perfectly reasonable. Every experiment available to the naked eye supported the idea. You could stand on a hilltop and uncover a lantern, and your friend on the next hilltop would see it appear without measurable delay. It took Galileo in the early 1600s to attempt the first real measurement. He positioned 2 people on distant hilltops with covered lanterns. The first person uncovered their lantern. The second, upon seeing the flash, uncovered theirs. Galileo hoped to measure the time delay. The result was inconclusive. Human reaction times swamped whatever signal delay existed. Light was too fast for the crude instruments of the Renaissance. But Galileo suspected the truth: light was fast, staggeringly fast, but not infinite. The first successful measurement came from an unlikely source. In 1676, the Danish astronomer Ole Romer was studying the moons of Jupiter. Specifically, he was timing the eclipses of Io, Jupiter's innermost large moon. Io disappears behind Jupiter at regular intervals, and Romer expected those intervals to be perfectly consistent. They were not. When Earth was moving away from Jupiter in its orbit, the eclipses arrived later than predicted. When Earth was moving toward Jupiter, they arrived earlier. Romer realized the discrepancy was not in Io's orbit, but in the travel time of light across the changing distance between Earth and Jupiter. He calculated a speed of roughly 220,000 kilometers per second, about 26% too low, but close enough to shatter the myth of instantaneous illumination. Light had a speed. It was measurable, and it was finite. Over the next 2 centuries, the measurement was refined. James Bradley used stellar aberration in 1728. Armand Fizeau used a spinning-toothed wheel and a mirror in 1849. Léon Foucault improved on Fizeau's method using a rotating mirror in 1862. Each experiment closed in on the same value. By the late 1800s, physicists knew the speed of light with impressive accuracy, but knowing the speed and understanding what that speed meant were two entirely different things. The late 19th century was dominated by a model of light that seemed obvious and elegant. Light was a wave. James Clerk Maxwell's equations of electromagnetism, published in 1865, showed that oscillating electric and magnetic fields propagated through space as waves, and that those waves travelled at exactly the speed of light. This was a triumph. Electricity, magnetism, and light were unified into a single framework, but waves need a medium. Sound waves require air, water waves require water. If light was a wave, what was it waving through? Physicists invented a substance to fill this gap. They called it the luminiferous ether, a perfectly transparent, perfectly rigid, perfectly stationary medium filling all of space. Light waves rippled through the ether the way sound ripples through air. The ether was undetectable by any direct means, but its existence seemed logically necessary. Without it, light had no medium. Without a medium, the wave model collapsed, so the ether was accepted as real, a foundational assumption of late 19th century physics, and then two men in Cleveland, Ohio destroyed it. In 1887, Albert Michelson and Edward Morley designed what would become one of the most important experiments in the history of science. The logic was clean. Earth orbits the Sun at roughly 67,000 miles per hour. If the ether is stationary and Earth moves through it, then the speed of light measured on Earth should differ depending on the direction of measurement. Light travelling in the same direction as Earth's motion should appear slightly slower, like swimming with a current, and light travelling perpendicular to Earth's motion should appear slightly faster. The difference would be small, but Michelson had built an instrument sensitive enough to detect it. His interferometer split a beam of light into two perpendicular paths, bounced each beam off a mirror, and recombined them. If the two beams travelled at different speeds, their recombination would produce an interference pattern, a series of light and dark fringes that would reveal the speed difference with extraordinary precision. They found nothing, zero difference, no interference shift, no ether wind, no variation of any kind, in any direction, at any time of day, at any time of year. The speed of light was the same in every direction. The ether did not exist. This result was catastrophic for classical physics, not mildly inconvenient catastrophic. The entire wave model of light depended on a medium that had just been shown to be fictional. But the implications went further. If the speed of light is the same regardless of the observer's motion, then something very deep about the universe is different from what Newton described. Under Newtonian physics, speeds add simply. If you stand on a train moving at 60 miles per hour and throw a ball forward at 30 miles per hour, the ball moves at 90 miles per hour relative to the ground. This works perfectly for baseballs and trains, but Michelson and Morley had shown it does not work for light. A beam of light emitted from a moving source does not travel at the speed of light plus the speed of the source. It travels at the speed of light, period. No addition, no subtraction. The same value, always, for everyone. For 18 years, the greatest minds in physics tried to explain this result without abandoning classical frameworks. Hendrik Lorentz, a Dutch physicist, proposed that objects physically contract in the direction of motion, that measuring rods literally shrink when moved through space, concealing the ether's effects. George Fitzgerald independently proposed the same idea. Henri Poincaré explored mathematical transformations that preserved the constancy of light speed. These efforts produced equations that worked the Lorentz transformations, but they lacked a physical explanation. They were mathematical patches applied to a crumbling foundation. Then in 1905, a 26-year-old patent clerk in Bern, Switzerland, did something no one else had the courage to do. He stopped trying to save the ether. He stopped trying to explain away the Michelson-Morley result. Instead, he accepted it as the starting point and asked what kind of universe would produce such a result. Albert Einstein published a paper titled "On the Electrodynamics of Moving Bodies." It contained no new experimental data. It proposed no new particles or forces. It simply took two postulates, two assumptions, and followed them to their logical conclusions. The first postulate stated that the laws of physics are the same in every inertial reference frame. No experiment performed in a uniformly moving laboratory can determine whether that laboratory is moving or stationary. The second postulate stated that the speed of light in a vacuum is the same for all observers, regardless of the motion of the source or the observer. That second sentence rewrote the universe. If the speed of light is truly constant for everyone, then the only way to accommodate this is for space and time themselves to be flexible, not rigid, not absolute, not the unchanging stage on which events play out, as Newton assumed. Space and time must stretch and compress depending on relative motion, adjusting themselves so that every observer, no matter how fast they are moving, measures the same speed for light. Consider a thought experiment that Einstein himself might have appreciated. You are standing on a train platform. A train passes by at a significant fraction of the speed of light. Aboard the train, a passenger has set up a simple clock. It consists of two mirrors, one on the floor and one on the ceiling, with a pulse of light bouncing vertically between them. Each round trip of the light pulse counts as one tick. From the passenger's perspective, the light bounces straight up and down. The distance between the mirrors is short. The ticks are quick. From your perspective on the platform, the situation looks different. The train is moving forward. The light pulse does not travel straight up and down, it follows a diagonal path. Up and to the right, then down and to the right, because the train has moved forward during the time the light travelled. A diagonal path is longer than a vertical path, but the speed of light is the same for both of you. If the light travels a longer distance at the same speed, it takes more time. The passenger's clock, as measured by you, ticks slower than your own clock. This is not a trick of observation. This is not caused by signal delays or visual distortions. This is time itself running at different rates for the two observers. The passenger experiences normal time aboard the train. You experience normal time on the platform, but your normals disagree. Time is not universal. It depends on your state of motion. This effect has a name time dilation, and it has a precise mathematical description. The ratio between the moving clock's rate and the stationary clock's rate is determined by a quantity called the Lorentz factor, represented by the Greek letter gamma. The formula takes the object's speed, divides it by the speed of light, squares the result, subtracts it from 1, takes the square root, and inverts it. At everyday speeds, cars, trains, airplanes, the result is so close to 1 that no clock on Earth could detect the difference without atomic precision. But as speeds climb toward the speed of light, the Lorentz factor begins to rise, slowly at first, then faster, then violently. At 10% of the speed of light, gamma equals approximately 1.005. Time dilation exists, but it is minuscule, about 0.5%. A clock aboard a ship moving at 10% of light speed would lose roughly 1 second for every 200 seconds, compared to a stationary clock. Barely noticeable, scientifically measurable, but experientially invisible. But let us pause on what 10% of light speed actually means in human terms. 10% of light speed is approximately 67 million miles per hour. The fastest object humanity has ever launched, NASA's Parker Solar Probe, which skims the outer atmosphere of the Sun, reached a peak velocity of roughly 430,000 miles per hour. That is fast enough to travel from New York to Los Angeles in under 20 seconds. It is the absolute pinnacle of human engineering in terms of raw speed, and it represents approximately 0.064% of the speed of light, not 6%. 0.064%. To reach 10% of light speed, you would need to travel 156 times faster than the fastest thing humanity has ever built. The energy required to accelerate even a small spacecraft to that velocity dwarfs any propulsion system currently in existence or serious development. And at that speed, after all that energy, all that engineering, all that technological triumph, time dilation is barely a rounding error. 0.5%. That is how steep the climb is. That is how far light speed sits above everything humans have achieved. Now pushed to 50% of the speed of light, 150 million meters per second, half of the cosmic speed limit. At this velocity, the Lorentz factor rises to approximately 1.155. Time aboard the ship runs about 13.5% slower than time at home. For every 100 seconds that elapse on Earth, only 86.6 seconds elapse aboard the ship. This is no longer negligible. Over the course of a year of Earth time, the ship's clock would fall behind by roughly 49 days. Nearly 2 months of time, simply gone experienced by neither the crew nor any instrument aboard the ship, but measurable by anyone watching from outside. Length contraction also becomes significant at 50% of light speed. This is the spatial counterpart to time dilation. Objects moving at relativistic speeds physically shorten in their direction of motion. Not optically, not as an illusion caused by light travel delays, but actually measurably shorter, as determined by any instrument in any reference frame. At 50% of light speed, a ship 100 meters long would measure approximately 86.6 meters from the perspective of an outside observer. The ship is compressed along the axis of motion. Its width and height are unchanged. Only its length contracts. This is not a theoretical curiosity. Length contraction was confirmed indirectly by the Michelson-Morley experiment itself, and directly by decades of particle physics. When protons are accelerated to high fractions of light speed in accelerators, their interaction cross-sections, the effective size they present to other particles, change in precisely the way length contraction predicts. The protons are physically contracted in their direction of motion. This is measured. This is used in calculations. This is real. At 50% of light speed, a third relativistic effect begins to assert itself with growing authority: the energy cost of further acceleration. In Newton's framework, kinetic energy scales with the square of velocity. Double your speed and your kinetic energy quadruples. This is clean, simple, and wrong at high velocities. Relativistic kinetic energy follows a different formula, one that includes the Lorentz factor. At low speeds, the relativistic formula reduces to Newton's formula. The two agree perfectly when velocities are small compared to light, but as speed climbs, the relativistic formula diverges upward. The energy required to accelerate an object grows faster than the square of velocity. It curves upward, bending toward a vertical asymptote at the speed of light. At 50% of light speed, the kinetic energy of a 1 kilogram object is approximately 24% higher than Newton's formula predicts. This might sound modest, but that 16% represents an enormous quantity of energy in absolute terms. The kinetic energy of 1 kilogram moving at 50% of light speed is approximately 1.4 times 10 to the 16th joules. For comparison, the nuclear weapon dropped on Hiroshima released approximately 6.3 times 10 to the 13th joules. A single kilogram at half-light speed carries roughly 220 times the energy of the Hiroshima bomb. And at this velocity, you have covered only half the distance to light speed, less than half, in terms of the energy still required to reach it. Here is where the distinction between Newton's universe and Einstein's begins to feel not just mathematically different, but viscerally different. In Newton's universe, if you have enough fuel, you can always go faster. Speed is limited only by engineering, by the thrust your engine produces and the mass you are pushing. There is no fundamental ceiling. You could, in principle, accelerate forever, reaching any velocity you desired. Einstein's universe does not work this way. As you approach the speed of light, each increment of additional speed costs disproportionately more energy than the last. The curve does not flatten, it steepens. Going from 0 to 50% of light speed requires a specific, enormous amount of energy. Going from 50% to 90% requires more than going from 0 to 50. Going from 90% to 99% requires more than going from 0 to 90%. The cost escalates so dramatically that the final fraction of a percent, the gap between 99.99999% and 100%, requires more energy than everything that came before, combined. In fact, it requires infinite energy, not a lot of energy, not an impractical amount of energy, infinite energy. And since infinite energy does not exist anywhere in the finite universe, the speed of light cannot be reached by any object with mass. But we are getting ahead of ourselves. At this point in the story, we are at 50% of light speed. The effects are real and measurable. Time dilation costs you 2 months per year. Length contraction squeezes your ship by 13%. The energy bill for further acceleration is already climbing in a way that Newton never imagined. And the Lorentz factor, currently a modest 1.155, is just beginning the steep part of its curve. Every single one of these effects has been measured in laboratories. Time dilation was confirmed directly in 1971, when physicists Joseph Hafele and Richard Keating placed cesium atomic clocks aboard commercial airliners and flew them around the world. Upon return, the airborne clocks disagreed with reference clocks on the ground by exactly the amount special and general relativity predicted, a combined offset of roughly 270 nanoseconds. The experiment was crude by modern standards, but unambiguous. Moving clocks tick slower. The global positioning system provides daily confirmation at a scale that affects billions of people. Each GPS satellite orbits Earth at approximately 14,000 kilometers per hour. The onboard atomic clocks experience time dilation due to their velocity, losing roughly 7 microseconds per day compared to ground clocks. They also experience a general relativistic effect. The weaker gravity at orbital altitude causes clocks to run faster by about 45 microseconds per day. The net effect is that satellite clocks gain approximately 38 microseconds daily. GPS software corrects for this. If it did not, positional errors would accumulate at roughly 10 kilometers per day. Every accurate GPS fix you have ever received is silent testimony that Einstein was right. Muons provide perhaps the most elegant confirmation. These subatomic particles are created when cosmic rays collide with atoms in the upper atmosphere at altitudes of roughly 15 kilometers. A muon at rest has a mean lifetime of approximately 2.2 microseconds. Even traveling at the speed of light, a muon should cover only about 660 meters before roughly 2/3 of any population decays. 15 kilometers is over 20 times that distance. Classical physics predicts that virtually no muons should reach the ground, yet ground-level detectors register thousands per minute. The explanation is time dilation. These muons travel at approximately 99.9% of light speed. Their Lorentz factor exceeds 22. From the muon's perspective, its internal clock ticks normally, but from Earth's perspective, that clock runs more than 22 times slower. The muon's effective lifetime, as measured by ground observers, stretches from 2.2 microseconds to over 49 microseconds, more than enough time to reach the surface. There is a beautiful complementary way to explain the same phenomenon from the muon's reference frame. From the muon's perspective, its lifetime is still 2.2 microseconds. It does not experience slow time, but the distance between the upper atmosphere and the ground is length contracted. 15 kilometers shrinks to roughly 670 meters from the muon's frame. The muon does not need a longer life, it needs a shorter distance, and the universe provides exactly that. Both explanations, time dilation from Earth's frame and length contraction from the muon's frame, yield identical predictions for how many muons reach the ground. Both are correct. Both are confirmed by experiment. They are two descriptions of the same underlying geometric reality, viewed from different angles through space-time. This is the world you enter when you begin to approach the speed of light. Not a world of science fiction tropes and dramatic explosions. A world where time is personal, where distance is negotiable, where the energy cost of motion curves upward toward a wall that no force in the universe can breach. Everything described here, time dilation at 10 and 50% of light speed, length contraction, the escalating energy demands, the experimental confirmations, is established science. Settled, measured, reproduced in laboratories and orbiting satellites and cosmic ray showers every single day. And yet, these effects at 10 and 50% are gentle compared to what lies ahead. The Lorentz factor at 50% is barely above 1. It rises politely, almost apologetically, like a curve that does not want to cause trouble. But past 50%, the curve changes character. It steepens, it accelerates. By 90% of light speed, gamma has climbed to 2.3. By 99%, it has reached 7.1. By 99.9%, it exceeds 22. By 99.99%, it surpasses 70. Each additional 9 after the decimal multiplies the Lorentz factor by roughly 3, and with it, every relativistic effect intensifies by the same factor. What happens in that steep section of the curve at 90%, 99%, and beyond transforms the experience from measurable distortion into something that would be utterly unrecognizable to human senses. Time does not just slow down, it nearly stops. Space does not just contract, it collapses into a narrow cone ahead. The energy cost does not just increase, it detonates, rising so fast that the entire energy output of a star becomes insufficient to push a single kilogram 0.01% faster. That is where this journey goes next. At 90% of the speed of light, you cross a threshold. Not a physical barrier, nothing blocks your path, no alarm sounds, no warning light flashes. The threshold is mathematical. It is the point where the Lorentz factor's curve abandons its gentle incline and begins climbing with a steepness that will not relent until it reaches vertical. Everything that was a curiosity at lower velocities, a clock running a fraction of a percent slow, a ship shortened by an amount too small to notice with the naked eye, now becomes an inescapable feature of your existence. The universe does not gently remind you that you are moving fast. It restructures itself around you. A clock aboard this ship ticks at less than half the rate of a clock on Earth. The crew eats breakfast. They read. They run diagnostics on their instruments. Every activity aboard feels perfectly normal in duration. But if they could peer through some impossible window and watch a clock back home, they would see it spinning at more than double speed. A conversation that takes 10 minutes aboard the ship consumes 23 minutes of Earth time. A night of sleep lasting 8 hours corresponds to over 18 hours at home. These are not cumulative errors that build up over months. This is the moment-to-moment rate of time. Every heartbeat aboard the ship skips more than one heartbeat at home. And the universe ahead has physically compressed. A star that rests 100 light-years away according to Earth's maps now measures approximately 43 light-years from the ship's instruments. The ship has not teleported closer. The space between the ship and the star has genuinely contracted from the ship's frame of reference. Every navigational chart drawn on Earth would be wrong aboard this vessel, not because of measurement error, but because distance itself has a different value depending on who is measuring it and how fast they are moving. But these quantitative changes, dramatic as they are, only begin to describe what 90% of light speed looks like. Step to the forward viewport of this hypothetical ship and look outside. The sky has changed. Stars that should be visible off to the sides, 45 degrees, 60 degrees from your direction of travel, have migrated forward. They appear clustered toward the front of the ship, as though the universe ahead is pulling them in. Stars behind you have thinned out. The rear hemisphere of the sky is growing darker, emptier. This is relativistic aberration, and it arises from the same geometry that causes a vertically falling raindrop to appear to slant toward you when you run through a storm. Your forward velocity changes the apparent angle at which incoming light arrives. At 90% of light speed, a star positioned at a true angle of 90 degrees from your direction of travel, directly to your side, appears to have shifted forward to roughly 26 degrees from the centerline. Almost everything in the sky has crowded toward the front. The colors have shifted as well. Stars ahead of you appear bluer than they should. Their light, arriving from a direction you are racing toward, gets compressed to shorter wavelengths. A yellow sun-like star in your forward field now glows with a harsh blue-white intensity. Stars farther from the centerline retain more of their natural color, but even they have drifted toward the blue end of the spectrum. Behind you, the opposite occurs. Stars in the aft sky have reddened. Their light is stretched to longer wavelengths as you race away from them. Dim red stars that were barely visible from Earth have shifted further into the infrared, vanishing from human perception entirely. The aft sky is not just emptier because of aberration, it is emptier because its remaining stars have been redshifted out of the visible spectrum. This is the relativistic Doppler effect operating across the entire sky simultaneously. It is not the simple Doppler shift you hear when an ambulance passes by. That acoustic version involves sound waves compressing ahead and stretching behind. The relativistic version involves space-time itself mediating the compression and stretching, incorporating time dilation into the frequency shift. At 90% of light speed, the combined frequency shift for a star directly ahead reaches a factor of approximately 4.4. Light that left that star as invisible infrared radiation arrives at the ship as visible blue light. Light that left as visible yellow arrives as ultraviolet. The ship's forward sky does not just look different, it radiates at different energies. Now accelerate to 95%. The Lorentz factor surges past 3. Time aboard the ship crawls at less than a third of the rate at home. 3 years elapse on Earth for every year the crew experiences. Length contraction crushes forward distances to roughly 32% of their rest values. A destination that Earth's maps place at 1,000 light-years now measures approximately 320 light-years from the ship's instruments. The visual distortions intensify. Relativistic aberration has now swept nearly the entire visible sky into the forward hemisphere. Stars that should lie behind the ship at true angles of 120 or 130 degrees from the direction of travel appear compressed into the forward half of the sky. The aft hemisphere is almost completely dark. A crew member turning around to look out the rear viewport would see a dim reddish haze where the faintest traces of heavily redshifted starlight still linger, surrounded by a deepening blackness that swallows everything. Ahead, the view has become something no human eye evolved to process. Stars concentrate into an increasingly tight disk, centered on the ship's direction of motion. The blue shift intensifies. Sun-like stars now appear as harsh ultraviolet sources that would damage unprotected eyes. Cooler red stars have shifted into the visible range, appearing as blue or white points that were previously invisible. The entire spectral identity of the forward sky has been remapped. A stellar cartographer aboard this ship would not recognize a single constellation. Every star has moved from its familiar position and changed its color. The sky is alien. There is a further effect compounding the visual transformation relativistic beaming, sometimes called the searchlight effect or headlight effect. When a light source moves toward an observer at relativistic speeds, its emitted radiation concentrates into a narrow forward cone. The faster the source moves, the tighter the cone. At 95% of light speed, starlight arriving from the forward direction is not only blue-shifted and aberrated, it is intensified. The energy flux from stars ahead appears magnified, making the forward sky significantly brighter than it would be for a stationary observer. Conversely, the aft sky dims further, as the radiation from stars behind is spread into a wider and weaker distribution. The ship appears to be flying into a spotlight, surrounded by gathering darkness. Now pushed to 99%. This is where the Lorentz factor enters a regime that breaks any remaining connection to everyday intuition. At 99% of light speed, every effect previously described does not merely continue, it multiplies. Time dilation stretches the ratio between ship time and Earth time, past 7 to 1. A crew member who boards the ship at age 30 and travels for a decade of their own life will return to find that over 70 years have passed on Earth. Their children will be elderly. Their grandchildren will be older than they are. The civilization they left behind may have transformed beyond recognition, and the crew member will have experienced none of it. They will have lived 10 ordinary years, morning routines, maintenance schedules, conversations over meals, while 7 decades of human history unfolded without them. Length contraction compresses the forward universe to roughly 14% of its rest measurement. A gap between stars that measures 100 light-years on an Earth-based chart shrinks to 14 light-years from the ship's frame. The entire Milky Way galaxy, 100,000 light-years across, would appear to be roughly 14,000 light-years wide from the ship's instruments. The universe has not moved. The stars have not shifted position relative to each other in any absolute sense. But the geometry of space-time, the fundamental fabric connecting distance and duration, has been reshaped by the ship's motion, and from inside that reshaping, the universe is a smaller place. The visual transformation at 99% approaches the surreal. Relativistic aberration has compressed essentially the entire sky into a narrow cone ahead of the ship. The half angle of this cone, the angular radius within which virtually all visible starlight concentrates, has shrunk to approximately 8 degrees. Imagine extending your arm and holding a tennis ball at arm's length. The disk of compressed starlight fits behind that ball. Everything outside that disk is darkness. The entire night sky, every galaxy, every nebula, every familiar constellation has been swept into a tiny blazing circle ahead, and a vast featureless void everywhere else. Within that circle, the light is extraordinary. Visible starlight has been blue-shifted into the ultraviolet and beyond. Stars that emit primarily in the infrared, stars too cool and dim to see with the naked eye under normal conditions, have been shifted into the visible spectrum, appearing as points of blue or white light that were never meant to be seen by human eyes. Meanwhile, the cosmic microwave background radiation, the faint afterglow of the Big Bang, normally invisible at a temperature of roughly 2.7 Kelvin, has been blue-shifted into the infrared range and is approaching the threshold of visibility. At higher velocities, this ancient light will shift further, from harmless relic to something far more dangerous. That transformation, and what it means for any material object at these speeds, belongs to the next chapter of this story. The Doppler shift at 99% produces a frequency multiplication factor of approximately 14 for objects directly ahead. A radio transmission from a stationary source at 100 MHz would arrive at the ship at 1.4 GHz. Visible light from a yellow star at a wavelength of 580 nanometers arrives compressed to roughly 41 nanometers deep in the extreme ultraviolet, far beyond what human eyes can detect. The forward sky is radiating at frequencies that would require specialized detectors to observe. A crew looking out the forward viewport with unshielded eyes would see nothing recognizable, just a searing point of light whose spectrum has been pushed beyond biology's capacity to interpret. Behind the ship, the situation inverts completely. The aft sky is functionally black. Every star behind the ship has been redshifted so far into the radio spectrum that no optical instrument aboard could detect them. The cosmic microwave background radiation arriving from the rear has been stretched to wavelengths so long they carry negligible energy. There is nothing to see. The crew might as well be staring into a cave. If the ship had no instruments, only eyes, the occupants would perceive themselves flying through a tunnel, a single blinding point of light ahead, absolute emptiness behind. The visual metaphor for approaching light speed is not a streaking starfield. It is a closing iris. Now let us reverse the perspective entirely. Forget what the traveller sees. Imagine you are standing on Earth with an impossibly powerful telescope, watching this ship recede at 99% of light speed. The first thing you notice is that the ship appears flattened. Length contraction is not a private experience, visible only from the ship's frame. It is also measured by outside observers. From your vantage point, the ship appears compressed to about 14% of its original length along its direction of travel. A vessel that measured 300 meters from nose to tail at rest now appears as a disc-like object, roughly 42 meters deep. Its width and height remain unchanged. The ship looks like it has been squeezed in a cosmic vice from the front and back. The ship's clock, if you could somehow read it through your telescope, would appear to tick at 1/7 its normal rate. Every process aboard the blinking of indicator lights, the movement of crew members past windows, the rotation of any mechanical component appears slowed by that same factor. A crew member waving at the viewport would appear to raise their arm over 7 times more slowly than normal. Not because they are moving in slow motion, but because the time in which their motion unfolds has been dilated from your perspective. Their experience is normal. Your observation of their experience is stretched. The light the ship emits also changes from your perspective. As the ship recedes, every photon it sends back toward you is redshifted. If the ship's beacon emits green light at 530 nanometers, you receive it stretched to roughly 7.4 micrometers deep in the mid-infrared, completely invisible to your eyes. The ship vanishes from optical telescopes. Only infrared and eventually radio instruments can track it. Its radio transmissions, originally at high frequencies, arrive stretched to lower frequencies. A voice message sent at normal pitch would arrive as a deep, slowed rumble, its frequency divided by that same Doppler factor. You would need to speed up the playback by a factor of 14 to hear intelligible speech. But suppose the ship were approaching you instead of receding. The Doppler effect reverses violently. Light from an approaching ship at 99% of light speed is compressed by a factor of 14. Green light arrives as extreme ultraviolet. The ship becomes invisible to optical telescopes not because it is dim, but because it is too energetic. Its radiation has been compressed into wavelengths that pass through glass and burn skin. The ship's infrared waste heat the background thermal emission from its hull arrives as visible light. The ship appears to glow, not from any internal illumination, but from the Doppler compression of its own thermal radiation. And the cosmic microwave background arriving at the ship from the forward direction, already blue-shifted from the ship's frame, appears from your frame to be arriving at the ship as a wall of high-energy radiation. You would calculate, correctly, that the forward-facing hull of the ship is being bathed in photons far more energetic than anything the ship's designers intended to shield against. Now consider what happens to communication between the ship and Earth as the velocity climbs. At the moment of departure, the crew can exchange messages with mission control normally. Signals travel at light speed in both directions. As the ship accelerates to 10%, then 20%, then 50% of light speed, the communication link degrades in ways that are subtle at first and devastating later. The first casualty is real-time conversation. Even at 10% of light speed, the ship moves fast enough that the round-trip signal delay grows noticeably within days. After a week at that velocity, the ship is roughly 11 billion miles from Earth, over 100 times the Earth-Sun distance. A radio signal takes roughly 17 hours just to reach the ship one way, and another 17 to return, assuming the ship held still. Since it continues racing away, the actual round-trip delay is even longer. Conversation becomes impossible. Communication collapses into a series of monologues, each one responding to questions asked nearly a day earlier. But the degradation goes beyond simple delay. The relativistic Doppler effect alters the signals themselves. As the ship accelerates past 50% of light speed, every transmission sent home is redshifted, stretched to lower frequencies, its information content arriving slower than it was transmitted. A 1-hour status report from the ship arrives at Earth stretched to approximately 1 hour and 44 minutes. This is the combined result of two effects operating together: time dilation slowing the ship's clock, and the increasing distance between ship and Earth stretching each successive wave crest further apart. Together, these effects produce the full relativistic Doppler shift. The ship's transmitter sends 1,000 cycles per second. Earth's receiver counts only 577. The voice of the crew slows. The data rate drops. Information arrives at a trickle compared to what was sent, From the crew's perspective, the reverse occurs for signals arriving from Earth. Transmissions sent from home arrive blue-shifted, compressed to higher frequencies, sped up, squeezed into shorter durations. A reply that Mission Control spent 1 hour composing arrives at the ship compressed into roughly 52 minutes. The voices sound slightly faster, slightly higher pitched. Data arrives in rapid bursts that the ship's systems must decompress and slow down for human consumption. As the ship pushes past 90% of light speed, these effects compound to the point where practical communication begins to fail. The crew's outgoing signals are redshifted by a factor exceeding 4. A voice transmission at standard frequencies arrives at Earth as a low-frequency drone at 1/4 the original frequency. Standard radio receivers cannot decode it without specialized processing. The data rate has collapsed to less than 1/4 of the transmitted rate. Transmitting a 1 megabyte file from the ship delivers less than 250 kilobytes per unit of Earth time. Meanwhile, the signal itself weakens not only because of distance, but because the redshift reduces the energy of each arriving photon. The ship's radio beacon, powerful at departure, fades to a whisper. At 99% of light speed, the situation becomes functionally terminal for any recognizable communication. The crew's transmissions arrive at Earth redshifted by a factor of 14. A voice signal is unrecognizable. A video feed is unwatchable without extreme computational reconstruction. The ship's outgoing data rate, as received by Earth, has collapsed to roughly 7% of the transmitted rate. And the signal is so faint, each photon carrying 1/14 of its original energy, that only the most sensitive radio telescopes on Earth or in Earth orbit could detect it at all. For all practical purposes, the crew has vanished. They continue to exist. They continue to transmit. But the universe has stretched their messages into ghostly murmurs that grow fainter and slower with every passing month. The crew experiences the mirror image of this silence. Signals from Earth arrive blue-shifted and compressed, but also increasingly delayed by the growing distance. A reply to one of their transmissions takes months, then years to arrive. When it does arrive, it carries news from a past that is already ancient by the ship's reckoning. The crew sent a question before breakfast. The answer arrives after they have aged 6 months. The answer itself was composed by engineers who have aged 3.5 years in the interim. The conversation is not slow. It is shattered, fragmented across diverging timelines that can never be reconciled while the ship remains at velocity. This communication collapse is not a technical failure. It is not caused by insufficient transmitter power or inadequate receiver sensitivity. It is a direct, unavoidable consequence of the Doppler effect and time dilation operating together at relativistic velocities. No amount of engineering can overcome it without violating the same speed limit that causes it. The ship and its home world are being separated not just by space but by the rate at which time flows. Their clocks diverge. Their signals distort. Their shared present dissolves into incompatible frames that can only be reconciled when the ship decelerates, which will not happen until the journey's end, years or decades later. The energy the ship carries is also visible in its effects. At 99% of light speed, the kinetic energy of the ship vastly exceeds its rest mass energy. A ship with a rest mass of 1,000 metric tons carries a kinetic energy equivalent to approximately 5.5 times 10 to the 23 joules. For scale, the total energy output of the Sun in 1 full second is approximately 3.8 times 10 to the 26 joules. This single ship, 1,000 metric tons, the mass of a small building, carries roughly the energy the Sun produces in 1.4 milliseconds. Every 14 ten-thousandths of a second, the Sun outputs the energy contained in this ship. The destructive potential of such an object arriving at a planet is beyond the scale of any natural disaster in recorded history. Now push past 99% into the territory that only particle accelerators have explored. At 99.9% of light speed, the Lorentz factor reaches approximately 22.4. 1 year of ship time corresponds to over 22 years at home. A crew that departs when their newborn children are in cradles returns to find those children older than themselves. Length contraction compresses forward distances to approximately 4.5% of rest values. A journey spanning 1,000 light-years on the map shrinks to roughly 45 light-years of subjective distance. The ship's instruments report that the destination is much closer than any Earth-based astronomer would claim. Neither measurement is wrong. They simply describe different slices through the same four-dimensional geometry. At 99.99% 4 nines, gamma reaches approximately 70.7. 1 year aboard the ship equals over 70 years at home. The forward sky has collapsed to a cone barely 1 degree wide. Virtually all electromagnetic radiation from the universe is concentrated into a searing pinpoint dead ahead. Behind, below, above, to every side nothing. Blackness so complete that it would be indistinguishable from floating in a sealed chamber with the lights off, except for that single incandescent point burning at the center of the forward viewport. The energy required to reach this velocity is not merely large, it operates on scales that render most human references meaningless. Accelerating a single kilogram to 99.99% of light speed requires approximately 6.3 times 10 to the 18th joules. This is equivalent to the energy released by roughly 1.5 billion metric tons of TNT, comparable to the simultaneous detonation of roughly 30 of the largest nuclear weapons ever tested, for 1 kilogram. A crude spacecraft massing thousands of tons would require energies that exceed the total energy consumption of human civilization across its entire history, multiplied many times over. And the most critical feature of this energy landscape is not its magnitude but its shape. The cost does not scale linearly with speed. It does not even scale with the square of speed, as Newtonian physics would suggest. It follows the Lorentz factor, which curves upward with increasing violence as velocity approaches c. Going from 0 to 90% of light speed costs a certain enormous amount of energy. Going from 90 to 99% costs more than the entire journey from 0 to 90. Going from 99 to 99.9% costs more than everything from 0 to 99. Each additional 9 after the decimal roughly triples the Lorentz factor, and with it, roughly triples the total energy requirement. The returns on each additional investment of energy measured in actual speed gain shrink towards 0. You pour in 3 times the energy and gain a fraction of a percent of additional velocity. To make this concrete, imagine a mission planning committee attempting to design a journey to a star system 50 light-years away. They have somehow solved the propulsion problem and possess a perfect matter-antimatter engine that converts 100% of fuel mass into directed kinetic energy, a theoretical ideal that no real engine could approach. At 90% of light speed, the journey takes roughly 56 years of Earth time and about 24 years of ship time. The kinetic energy alone equals roughly 1.3 times the ship's rest mass energy. But a rocket must carry its fuel, and that fuel must also be accelerated. The relativistic rocket equation for a perfect photon drive accelerating to 90% of light speed and decelerating back to rest at the destination demands a mass ratio of roughly 19 to 1. For a 1,000-ton ship, that means approximately 18,000 tons of matter-antimatter fuel consumed during the journey. Enormous, but at least expressible in human terms. Now the committee wants to cut the ship time in half. Reaching 99% of light speed would reduce ship time to approximately 7 years for the same 50 light-year journey. But the fuel requirement does not merely double. The relativistic rocket equation punishes exponentially. For the same photon drive accelerating to 99% and decelerating to rest, the mass ratio climbs to roughly 200 to 1. For a 1,000-ton ship, that means approximately 200,000 tons of matter-antimatter fuel over 10 times the fuel budget of the 90% mission for a speed increase of just 9 percentage points. And that fuel itself must be accelerated along with the ship, which means the actual mass ratio is worse. Exponentially worse, because the fuel needed to accelerate the fuel must also be fueled. The rocket equation, even for a perfect engine, demands mass ratios that grow exponentially with the desired velocity change. At 99% of light speed, The practical fuel mass dwarfs the payload by factors that make the entire concept borderline absurd, even in the theoretical limit. Pushed to 99.9%, and the situation becomes truly hopeless from any engineering standpoint currently imaginable. The fuel-to-payload ratio climbs into the tens of thousands. You would need to convert the mass of a small moon into directed energy to accelerate a single crewed vessel, and every fraction of a percent beyond that demands another multiplication. The energy exists in the universe, stars produce it, supernovae release it, black holes store it but concentrating it, directing it, and sustaining it for the duration of a multi-year acceleration is a challenge so far beyond current capability that placing a timeline on its solution is meaningless. At 99.9999% 6 nines, the Lorentz factor exceeds 700. 1 year of ship time spans over 7 centuries at home. The crew could cross the entire Milky Way galaxy in a subjective time span shorter than a typical human career, but over 100,000 years would pass on Earth during that crossing. Everyone and everything the crew knew would be long gone. Civilizations would have risen and fallen. The stars themselves would have visibly shifted position. These numbers are not aspirational engineering targets. They are mathematical certainties within Einstein's framework, confirmed by the behavior of particles in accelerators that reach these exact velocity regimes every day. Protons in the Large Hadron Collider circulate at velocities so close to light speed that their Lorentz factor exceeds 7,000. They carry thousands of times more energy than their rest mass, yet they never reach the limit. The next section explains precisely why. The behavior of these protons illustrates something crucial about the approach to light speed. Each successive 9 after the decimal point costs dramatically more energy than the last, while delivering diminishing incremental increases in actual speed. Going from 99% to 99.9% of light speed, an increase of 0.9 percentage points requires roughly 3 times more energy than going from 0 to 99% in the first place. Going from 99.9 to 99.9, 9%, an increase of 0.09 percentage points, requires roughly another tripling. The energy cost per unit of additional speed is not just increasing, it is accelerating. The curve bends upward without limit, asymptotically approaching a vertical wall at exactly the speed of light. This asymptotic behavior is not a quirk of the equations. It is the equations telling us something fundamental about the structure of reality. The universe is configured so that massive objects cannot reach the speed of light, not because of insufficient technology, but because the very fabric of space-time makes the energy cost infinite at that boundary. The gap between 99.9999% and 100% of light speed is not a gap that more fuel can close. It is not a barrier that a better engine can break through. It is a feature of the geometry of the universe, as immovable as the fact that parallel lines on a flat plane never meet. You can approach it asymptotically, getting closer and closer without ever touching it, like a curve that forever bends toward a line it can never reach. And yet the effects you experience during that approach are extraordinary. All of this is confirmed. All of this is real. And all of this happens before you reach the wall, before you confront the final, absolute impossibility of that last infinitesimal gap between almost and exactly the speed of light. What waits at that wall, and why no amount of energy in the entire observable universe can carry you across it, reveals the deepest truth about why light speed is not just fast, it is forbidden. All of this is confirmed. All of this is real. And all of this happens before you reach the wall, before you confront the final, absolute impossibility of that last infinitesimal gap between almost and exactly the speed of light. What waits at that wall, and why no amount of energy in the entire observable universe can carry you across it, reveals the deepest truth about why light speed is not just fast, it is forbidden. There is an equation at the heart of this entire story. It is not hidden in some obscure appendix of a theoretical journal. It is not the subject of ongoing debate. It sits in every undergraduate physics textbook published in the last century, verified by more experimental data than almost any other formula in science. And it contains, within its simple structure, the reason no object with mass can ever reach the speed of light. The equation describes the total energy of a moving object. It states that the total energy equals the Lorentz factor multiplied by the rest mass of the object multiplied by the speed of light squared. Written in notation, E equals gamma times m times c squared. When the object is stationary, gamma equals 1, and the equation reduces to the most famous formula in physics, E equals mc squared. That version describes the energy locked inside mass itself. The full version describes the total energy of a moving object, rest energy plus kinetic energy combined. The critical detail is gamma, the Lorentz factor, the quantity that starts near 1 at low speeds and climbs as velocity increases. At 90% of light speed, gamma is 2.3. At 99%, 7.1. At 99.9%, 22.4. The previous sections traced this climb in detail, but the equation reveals something that no amount of describing the climb can fully capture: what happens to gamma at exactly the speed of light. Plug in V equals C. The ratio V over C becomes 1. 1 squared is 1. 1 minus 1 is 0. The square root of 0 is 0. And 1 divided by 0 is undefined, or, in the language of limits, infinity. Gamma does not merely become large at the speed of light, it ceases to be a finite number. It diverges. It breaks. This means the total energy required to accelerate any object with mass to the speed of light is infinite, not metaphorically infinite, not practically infinite in the way that people say a task would take forever when they mean it would take a very long time. Mathematically, formally, rigorously infinite. The energy function has a vertical asymptote at V equals C. No finite value of energy, no matter how astronomical, reaches that asymptote. You can pour in the energy equivalent of a planet, a star, a galaxy, the entire observable universe. The result moves the velocity closer to C, but never reaches it. The gap narrows, but never closes. The curve bends toward the asymptote and follows it upward without ever touching it, like a hyperbola approaching its axis. This is not an artifact of approximation. It is not a quirk of one particular mathematical framework that a different formulation might avoid. The Lorentz transformation is embedded in the metric structure of Minkowski spacetime, the four-dimensional geometric framework that underlies all of special relativity. The vertical asymptote at C is a geometric feature of spacetime itself. It is as intrinsic to the universe as the fact that the circumference of a circle relates to its diameter by the constant pi. You cannot negotiate with it. You cannot engineer around it. You cannot accumulate enough resources to overcome it, because overcoming it would require a quantity that does not exist in any finite universe. The experimental evidence for this asymptotic behavior is not indirect or circumstantial. It is direct, precise, and repeated billions of times per year. Every particle accelerator on Earth is a laboratory demonstration of the wall. Consider what happens during the final stages of acceleration at a facility like CERN. Protons enter the main ring, already travelling above 99% of light speed. The enormous superconducting magnets and radio frequency cavities then pour additional energy into the beam megajoules per beam, sustained over minutes of continuous acceleration. The protons absorb this energy, but they do not meaningfully speed up. Their velocity inches from 99.97% toward 99.999991%, a change so small that if you wrote both numbers out to 5 decimal places, they would appear identical, yet the energy each proton carries increases by a factor of thousands. All of that energy goes into increasing the proton's effective inertia. The proton resists acceleration more and more fiercely as it approaches the limit. It behaves as though it is getting heavier, not because new mass is being added, but because the relationship between energy and velocity at relativistic speeds is fundamentally nonlinear. Energy added near the speed of light converts almost entirely into resistance to further acceleration rather than into additional speed. This has been measured with precision that leaves no room for ambiguity. The mass-energy equivalence of relativistic particles is confirmed every time two protons collide at the LHC and produce a shower of new particles whose total mass exceeds the rest mass of the original protons by enormous factors. The excess mass comes from kinetic energy converted into matter during the collision, a direct, measurable, repeatedly verified consequence of E equals mc squared operating in the relativistic regime. The energy is real, the mass increase is real, and the asymptote at C holds with the same certainty as any measured quantity in physics. But the most extreme natural demonstration of this wall did not come from a laboratory. It arrived from outer space. On the 15th of October, 1991, a cosmic ray detector in Dugway, Utah registered a single subatomic particle, a proton traveling at a velocity so close to the speed of light that the measurement pushed the limits of scientific notation. This particle, later dubbed the Oh My God particle, written as a fraction of c, the difference between its velocity and light speed was roughly 5 times 10 to the negative 24th. The Lorentz factor exceeded 320 billion. The kinetic energy of this single proton, a particle with a rest mass of roughly 1.7 times 10 to the negative 27 kilograms, was approximately 50 joules. That is the energy of a baseball thrown at roughly 60 miles per hour, concentrated in a single subatomic particle. 50 joules is enough to lift a small textbook from the floor to a table. All of that energy carried by an object so small that trillions of them could fit on the head of a pin. And despite this almost incomprehensible energy, despite being accelerated by the most violent astrophysical processes the universe can produce, perhaps the jets of active galactic nuclei or the shock fronts of relativistic supernovae, the particle was still not travelling at the speed of light. The gap between its velocity and c was unimaginably thin. If you expressed its speed as a decimal and tried to find the first digit that differed from the speed of light, you would need to go past 20 decimal places. But the gap existed. It was non-zero, and closing it that last, inconceivably small remaining fraction would have required more energy than any process in the observable universe could supply. This is not a matter of insufficient cosmic power. The observable universe contains an estimated 4 times 10 to the 69 joules of total mass energy. Convert every galaxy, every star, every particle, every photon, every trace of dark matter and dark energy into pure kinetic energy directed at a single proton, and the proton would move closer to C by an absurd number of additional 9s, but it would not reach it. The remaining gap, no matter how submicroscopic, requires infinite energy to close, and infinity exceeds any finite quantity by definition, not by a lot, not by a calculable margin, but categorically. Finite and infinite are different kinds of numbers. You cannot bridge the gap between them by adding more. Now set aside the energy argument not because it is wrong, but because it is not the only consequence of approaching the wall. Ask a different question. Suppose some unknown physics or some hypothetical energy source could push a material object arbitrarily close to light speed. What would happen to the object itself? What would matter experience at velocities so extreme that the Lorentz factor reaches into the thousands or millions? The answer begins with radiation. Empty space is not empty. The cosmic microwave background radiation, the thermal afterglow of the Big Bang, permeates every cubic centimetre of the universe. Its photons are everywhere, travelling in every direction, filling space with a faint bath of microwave frequency radiation at a temperature of approximately 2.7 Kelvin. Under normal conditions, this radiation is harmless and nearly undetectable without specialized instruments. Its photons carry tiny energies, corresponding to wavelengths of roughly 1 to 2 millimeters. They pass through most materials without interaction. You are being bathed in cosmic microwave background photons right now, and will never notice. But from the reference frame of a ship traveling at extreme relativistic velocity, these photons are transformed. The relativistic Doppler effect compresses the wavelength of every photon arriving from the forward direction. At 99.9% of light speed, microwave photons with rest frame wavelengths of 1 mm arrive at the ship compressed to wavelengths of roughly 22 micrometers, well into the infrared. Still not dangerous. But at 99.99%, the compression pushes those same photons into the near-infrared, approaching visible wavelengths. At 99.999%, they arrive as visible light. The ship begins to glow from the perspective of its own crew, not from any internal source, but from the ancient light of the Big Bang being squeezed into visibility. Continue accelerating. At 99.9999%, the cosmic microwave background photons arrive as ultraviolet radiation. At 99.99999%, they have been compressed into X-rays. At the velocities achieved by the oh my god particle, those same gentle microwave photons arrive as ultra-high energy gamma rays, each individual photon carrying enough energy to disrupt atomic nuclei. This is not a peripheral concern. The cosmic microwave background is isotropic. It fills all of space uniformly. A ship traveling at extreme relativistic speeds faces this radiation from every forward-facing angle simultaneously. The forward hemisphere of the sky becomes a wall of increasingly energetic photons, their intensity magnified by relativistic beaming, their energy amplified by the Doppler shift. At sufficiently high velocities, the radiation flux from the cosmic microwave background alone exceeds the output of a nuclear reactor directed at the ship's forward hull. No known material can withstand indefinite bombardment by gamma rays at this intensity. The hull would heat, degrade, and eventually ablate atoms stripped from the surface layer by layer. But the cosmic microwave background is only the beginning of the radiation problem. Interstellar space contains matter sparse, but not absent. The average density of the interstellar medium in our galaxy is approximately 1 hydrogen atom per cubic centimeter. At rest, these atoms are harmless. A single hydrogen atom drifting through space carries negligible kinetic energy, but from the frame of a relativistic ship, these stationary atoms are transformed into a relativistic particle beam aimed directly at the hull. At 99% of light speed, each hydrogen atom encountered by the ship carries kinetic energy from the ship's frame of approximately 6 times the proton's rest mass energy. That translates to roughly 6 billion electron volts per atom, comparable to the energy of particles produced in medical proton therapy accelerators, which are specifically designed to destroy tissue. At 99.9%, the energy per atom exceeds 20 billion electron volts. At 99.99%, it surpasses 65 billion electron volts, approaching the per-particle energies in some of the highest energy laboratory experiments ever conducted. A ship traversing interstellar space at these velocities would encounter roughly 30 billion hydrogen atoms per second for every square centimeter of forward-facing hull area. Each atom carries the energy of a cosmic ray. The cumulative flux constitutes a continuous particle beam of extraordinary intensity. When these atoms strike the hull, they do not bounce off, they penetrate. Relativistic protons interact with the nuclei of whatever material they encounter, producing cascades of secondary particles, pions, muons, kaons, gamma rays that penetrate deeper into the ship's structure. These secondary particles irradiate everything they pass through. Electronics fail, structural materials weaken, biological tissue absorbs lethal doses in fractions of a second. Shielding helps, up to a point. Dense materials like lead or tungsten can absorb some of the secondary particle cascades. Magnetic fields might deflect charged particles before they reach the hull. Hydrogen ice shields positioned ahead of the ship could serve as sacrificial buffers, absorbing impacts while being gradually eroded. But every shielding strategy has a velocity threshold above which it fails. The higher the ship's speed, the more energetic each incoming particle becomes, and the deeper the resulting cascade penetrates. At velocities beyond 99.99%, the energy per incoming hydrogen atom exceeds what any practical shielding depth can fully absorb. The ship is being sandblasted by a relativistic wind that grows more destructive with every incremental increase in speed. There is also a thermal problem. Every particle impact deposits energy in the hull as heat. At extreme velocities, the energy deposition rate exceeds what any radiative cooling system can dissipate. The hull temperature rises, materials soften, structural integrity degrades. At some threshold velocity, the forward surface of the ship simply melts, not from engine heat or atmospheric friction, but from the accumulated kinetic energy of interstellar hydrogen atoms striking it at nearly the speed of light. These are not speculative scenarios. They are straightforward applications of known physics, relativistic kinematics, nuclear interaction cross-sections, radiation transport calculations applied to the well-measured properties of the interstellar medium and the cosmic microwave background. The numbers have been calculated by multiple research groups. The conclusions are consistent. A material object attempting to travel at velocities above roughly 99.99% of light speed faces a radiation environment that would destroy any known structure within hours or days, regardless of shielding. This means that the wall is not only an energy barrier, it is also a survivability barrier. Even in a hypothetical scenario where infinite energy was somehow available, the material object being accelerated would disintegrate before reaching the speed of light. The universe does not merely make it impossible to reach C through energy requirements. It makes the approach itself lethal at sufficiently high velocities. The closer you get, the more hostile the environment becomes, and the hostility scales without bound, just like the energy cost. Now, a crucial clarification must be made, because it is the source of more public confusion about light speed than perhaps any other single point. Photons travel at the speed of light. This is an established fact. Every photon ever emitted by a candle, a laser, a distant quasar, travels at exactly 299,792,458 meters per second in a vacuum. If massive objects cannot reach this speed, how do photons manage it? The answer is that photons do not manage it. They do not accelerate to light speed. They do not start at rest and build up velocity. They are born at light speed and exist at light speed for their entire existence. A photon has zero rest mass. When you plug zero mass into the Lorentz factor equation, the formula that produces infinity for any non-zero mass becomes irrelevant. Photons do not use the same energy-velocity relationship as massive objects. Their energy is determined entirely by their frequency. E equals h times f, where h is Planck's constant and f is the frequency. A photon can have any energy, from the tiniest radio wave to the most energetic gamma ray, and it always travels at exactly c. This is not a loophole. It is a completely separate mode of existence within space-time. Massive particles follow time-like paths through space-time paths, along which proper time accumulates, clocks tick, and aging occurs. The faster a massive particle moves through space, the slower it moves through time, but it always moves through both. Massless particles follow null paths, trajectories along which proper time is exactly zero. A photon does not experience duration. It does not have a rest frame. The concept of a photon's perspective is not well defined within the mathematical framework of special relativity. Asking what a photon experiences is like asking what lies north of the North Pole. The question uses familiar words but points to a location that does not exist within the coordinate system. This distinction between massive and massless particles is not a minor technical detail. It is the reason the speed of light exists as a limit in the first place. Space-time is structured so that massive objects trace one category of path and massless objects trace another. The speed of light is the boundary between these two categories. It is not a speed that massive objects can reach by going faster. It is a different kind of trajectory that massive objects are geometrically excluded from following. Just as a curve on the surface of a sphere cannot become a straight line in three-dimensional space, no matter how you deform it. The two belong to different geometric categories. This geometric perspective reveals something profound about the nature of the wall. It is not imposed on the universe from outside, the way a government imposes speed limits on highways. It is woven into the metric of space-time, the mathematical object that defines how distances and durations relate to each other across all four dimensions. It is the ratio that makes the space-time interval invariant for all observers. Without it, causality collapses. Effects could precede causes. The orderly sequence of events that makes physics predictable would dissolve into chaos. Think of it this way. In ordinary space, the shortest distance between 2 points is a straight line. This is not a rule someone decided on. It is a consequence of the geometry of flat space. Similarly, in space-time, the fastest possible signal between two events travels at the speed of light. This is not a rule imposed on signals. It is a consequence of the geometry of Minkowski space-time. Breaking the speed of light would not be like exceeding a speed limit. It would be like drawing a straight line shorter than the shortest possible distance between 2 points. The concept itself is self-contradictory within the geometry that defines it. The comparison to the sound barrier, which appears frequently in popular discussions, is therefore deeply misleading. The comparison to the sound barrier, which appears frequently in popular discussions, is therefore deeply misleading. The sound barrier was a property of air, a medium-dependent phenomenon that varied with temperature and altitude. Engineers built stronger aircraft with swept wings and more powerful engines, and Chuck Yeager crossed it in 1947. The speed of light depends on no medium. It is a property of space-time's geometry itself, and no advance in engineering changes geometry. It is woven into the fabric of reality at the deepest level physics has ever probed. Every experimental test from Michelson-Morley to GPS satellites, to the Large Hadron Collider, to the oh my god particle confirms the same conclusion. The wall at sea is absolute, and yet this absoluteness carries a strange and often overlooked corollary. The wall forbids reaching light speed. It does not forbid approaching it. There is no minimum distance you must maintain from the limit. You can get as close as energy permits 99%, 99.999%, 99.999999999%. Each step closer costs more than the last. Each step produces more extreme time dilation, length contraction, and environmental hostility. But there is no secondary barrier that stops you from pushing nearer. The universe does not enforce a buffer zone around C. It simply ensures that the final step from asymptotically close to exactly equal is the one step that requires more than exists. This asymptotic accessibility is not a consolation prize. It is, in a surprising and counterintuitive sense, the reason interstellar travel remains physically possible within Einstein's framework. The very time dilation that makes the approach to light speed so strange also compresses the subjective duration of interstellar journeys. The faster you travel, the less time the journey takes from your perspective. Not because you are covering distance faster in any absolute sense, your speed never exceeds c, but because the distance itself contracts and your personal clock slows down. At 99.9999% of light speed, a journey spanning 1,000 light-years of Earth-measured distance would require roughly 1.5 years of ship time. You would arrive having aged less than 2 years while a millennium passed at home. The wall prevents you from reaching C, but it does not prevent you from harvesting the effects of getting close. Time dilation is not just a penalty, it is a tool. Length contraction is not just a distortion, it is a shortcut. The same physics that makes light speed forbidden makes near light speed extraordinarily powerful for any civilization willing to pay the energy cost and accept the temporal consequences. The question that remains, the question this entire journey has been building toward, is what this wall actually means. Not for protons in accelerators or hypothetical spacecraft or abstract equations. What does it mean for beings like us, who evolved under the gentle physics of a rocky planet orbiting an ordinary star, and who now look upward at a universe separated from us not by distance alone, but by the deepest structural rule that reality enforces. The answer lies not in what the wall forbids, but in what it reveals about the cosmos we inhabit and the terms on which it permits us to explore it. Every generation produces a version of the same dream. Warp drives, hyperspace tunnels, jumps through folded dimensions. The fantasy of outrunning light has embedded itself so deeply in human culture that many people assume it is only a matter of time before some breakthrough renders Einstein obsolete, the way Einstein rendered Newton incomplete. The assumption feels reasonable. History is filled with confident declarations of impossibility that were later overturned. Lord Kelvin declared heavier-than-air flight impossible. Astronomers insisted humans would never know the chemical composition of stars. Respected physicists argued that nuclear energy could never be harnessed. Each time, reality proved more accommodating than the pessimists predicted. Why should light speed be any different? The answer is that light speed occupies a fundamentally different category of limit than any of those historical examples. Kelvin was wrong about flight because he misjudged engineering. The physics of aerodynamic lift was already well understood, and building a machine that exploited it was a matter of materials and design. Astronomers were wrong about stellar composition because they failed to anticipate spectroscopy, a new observational technique that accessed information they assumed was unreachable. Physicists were wrong about nuclear energy because they underestimated the practical implications of equations they already possessed. In every case, the supposed impossibility was rooted in a failure of imagination about technology or methodology, not in the fundamental structure of physical law. The speed of light is different. It is not a technological barrier. It is not a limitation of current instruments or materials. It is a geometric property of the space-time manifold, the four-dimensional arena in which all events occur. Saying that future technology might break the light speed barrier is not analogous to saying that future aircraft might break the sound barrier. It is analogous to saying that future mathematicians might discover a triangle whose interior angles sum to 200 degrees on a flat plane. The statement is not pessimistic. It is incoherent. It asks for something that contradicts the definitions of the terms involved. This does not mean physics is finished. It does not mean no new discoveries remain. Science always holds open the possibility that deeper theories will supersede current ones. General relativity itself superseded Newtonian gravity, revealing that what Newton described as a force was actually the curvature of space-time caused by mass and energy. Some future theory, perhaps a successful quantum theory of gravity, might reveal that space-time has a deeper structure than Einstein described. That deeper structure might, in principle, permit phenomena that current physics forbids. But here is the constraint that any such future theory must satisfy. It must reproduce every prediction of special relativity within the domains where special relativity has been tested. And special relativity has been tested across an extraordinary range of conditions, from the slow drift of GPS satellites to the violent collisions of particles at 99.999991% of light. Speed. Any successor theory must agree with Einstein's equations to the precision of those experiments, which in many cases exceeds 1 part in a billion. This means the speed of light limit cannot simply be discarded by a future theory. It must be preserved as a limiting case, the way Newtonian gravity is preserved as a limiting case of general relativity at low masses and slow speeds. Whatever deeper physics might exist, it must reduce to Einstein's framework under normal conditions. The wall at sea will remain in every regime where current experiments have confirmed it. Some theoretical proposals do explore geometries that might, under exotic conditions, permit effective faster-than-light travel without violating special relativity locally. The most famous is the Alcubierre warp metric, proposed in 1994 by the Mexican physicist Miguel Alcubierre. His solution to Einstein's field equations describes a bubble of warped space-time that compresses space ahead of a ship and expands space behind it. The ship itself remains stationary within the bubble, never exceeding the local speed of light. But the bubble moves through the surrounding space-time at an arbitrarily high effective velocity, carrying the ship along like a surfer on a wave. The mathematics is valid. The solution satisfies the field equations of general relativity, but the physical requirements are devastating. The Alcubierre metric requires a form of energy with negative energy density, a substance whose gravitational properties are the opposite of normal matter. While quantum field theory permits tiny negative energy densities under very specific conditions, such as the Casimir effect between closely spaced metal plates, the amount required by the Alcubierre drive exceeds anything quantum mechanics can plausibly supply. Early calculations suggested the energy requirement was equivalent to the entire mass energy of the observable universe, but with a negative sign. Later refinements by other researchers reduced the estimate dramatically in some configurations to roughly the mass energy of Jupiter, but the need for exotic matter with properties no known substance possesses remains. No experiment has ever produced or detected negative energy density in the quantities required. No theoretical framework has demonstrated that such quantities can exist in a stable, controllable form. Traversable wormholes face similar obstacles. These hypothetical tunnels through spacetime, connecting distant points via a shortcut through a higher dimensional geometry, are permitted by the mathematics of general relativity. But keeping a wormhole open and traversable requires exotic matter that violates the energy conditions' mathematical constraints that ensure gravity behaves attractively under normal circumstances. Without exotic matter, a wormhole either never forms or collapses faster than anything can pass through it. The exotic matter requirement is not a minor technical detail. It is a fundamental obstacle that no known physics can address. These proposals are valuable as theoretical explorations. They map the boundaries of what general relativity permits and illuminate the connections between space-time geometry, energy, and causality. But they are not engineering blueprints. They are not paths toward practical faster-than-light travel waiting for technology to catch up. They are mathematical possibilities that require physical ingredients the universe may not supply. Treating them as evidence that light speed can be circumvented is like treating the mathematical existence of negative numbers as evidence that you can possess negative apples. The honest scientific assessment, as of everything confirmed through experiment and observation, is this. The speed of light is an absolute limit for any object carrying mass, or any signal carrying information. No known mechanism for exceeding it has been demonstrated, detected, or experimentally validated. This assessment might change if revolutionary new physics is discovered. But it has not changed yet, and the experimental evidence supporting the current limit is among the most robust in all of science. So what does this mean for a species that evolved on a single planet and dreams of reaching the stars? It means the stars are reachable, but not on the terms most people imagine. The same time dilation that makes light speed unattainable transforms interstellar travel from impossible to merely extraordinary. Consider a ship that accelerates at 1 g, 9.8 meters per second squared, the same gravitational pull you feel standing on Earth's surface. This acceleration profile is special because it provides the crew with a comfortable environment. They walk normally, objects fall as expected, their bodies experience no unusual mechanical stress. 1 g of sustained acceleration is the gentlest possible interstellar trajectory for human physiology. At 1 g of constant acceleration for the first half of the journey, and 1 g of constant deceleration for the second half, a symmetric acceleration profile that brings the ship to rest at its destination. The numbers are remarkable. Alpha Centauri, the nearest star system at roughly 4.4 light-years, could be reached in approximately 3.6 years of ship time. Earth would experience about 6 years during the crossing. The peak velocity at the midpoint would approach 95% of light speed. The crew would age 3.6 years. Their families at home would age 6 years. The gap is noticeable but not devastating. A round trip with turnaround time would consume perhaps 8 years of the crew's life and 13 years of Earth time. This is within the range of human experience comparable to a long military deployment or an extended research expedition to a remote location. Extend the journey to an intermediate distance, a star cluster roughly 1,000 light-years from Earth. At 1 g of sustained acceleration and deceleration, the crew would experience approximately 13.5 years of ship time. 13.5 years. A crew member who departed at 30 would arrive at 42. They would have lived through a period equivalent to completing 2 university degrees back-to-back. They would have celebrated a dozen birthdays aboard the ship, maintained equipment through hundreds of routine cycles, and watched the bizarre visual effects of near-light speed travel evolve outside their viewports across the full arc of acceleration, cruise, and deceleration. But upon arrival, approximately 1,002 years would have passed on Earth. Every empire that existed at departure would have risen, peaked, declined, and been forgotten. The languages spoken by mission control would be as dead as Old English is to a modern speaker. The crew would step off their ship into a millennium they had no part in building strangers, to a future that began the moment they left. This intermediate example reveals the emotional core of relativistic travel more starkly than either the short hop to Alpha Centauri or the grand crossing to another galaxy. At 4 light-years, the time gap is manageable. The crew can imagine returning to people they know. At galactic scales, the gap is so vast it becomes abstract. No one pretends a round trip is possible. But at 1,000 light-years, the gap falls in a cruel middle ground. 1,000 years is long enough to erase everything familiar, but short enough to feel personal. The crew would know concretely and specifically that every person they loved died centuries ago, that the music they grew up with is now ancient history, that the news they followed, the politics they debated, the friendships they cherished are not just over but archaeologically distant. 12 years of their lived experience purchased a one-way ticket across 10 centuries of everyone else's. Now extend the journey further. The center of our galaxy lies approximately 26,000 light-years from Earth. At 1 g of sustained acceleration and deceleration, a ship could reach it in roughly 20 years of ship time. 20 years. A crew that departed in their mid-20s would arrive in their mid-40s, biologically healthy, having experienced 2 decades of life aboard a ship. They would have eaten thousands of meals. They would have exercised, argued, celebrated birthdays, mourned losses, read books, maintained equipment, and watched the universe transform through their viewports. 20 years of genuine human experience. But when they arrived, approximately 26,000 years would have passed on Earth. The civilization that launched them would be as distant as the earliest permanent human settlements are to us. Every language they spoke would be extinct. Every institution they served would be forgotten. Every person they loved would have been dead for hundreds of generations. The travelers would arrive in the deep future, strangers in a galaxy that had moved on without them. Push further still. The Andromeda Galaxy, our nearest major galactic neighbour, lies roughly 2.5 million light-years away. At 1 g of constant acceleration and deceleration, the journey would require approximately 28 years of ship time. 28 years. Less than 3 decades of subjective human experience to cross an intergalactic void so vast that light itself requires 2.5 million years to span it. The crew would arrive biologically middle-aged, and approximately 2.5 million years would have passed at their point of origin. The species that launched the ship might no longer exist in any recognizable form. The sun would still burn. It has roughly 5 billion years of fuel remaining, but Earth's continents would have drifted. Its climate would have shifted through multiple ice ages, and its biosphere would have evolved in directions no biologist alive today could predict. These calculations are not approximations or optimistic estimates. They are exact solutions to the relativistic equations of constant proper acceleration, derived directly from special relativity's framework, and confirmed by every experiment that has tested time dilation. The mathematics is settled. The question is not whether these journeys are physically possible under the laws of the universe. The question is whether any civilization could summon the engineering capability to attempt them. The energy requirements are formidable. Accelerating a ship at 1G for years requires a propulsion system of extraordinary power and efficiency. The most energetically efficient conceivable engine, a perfect matter-antimatter annihilation drive that converts 100% of fuel mass into directed thrust, would require quantities of antimatter that exceed current global production by a factor that defies meaningful comparison. Humanity currently produces antimatter in quantities measured in nanograms per year. An interstellar mission would require tons, billions of times more than our total historical production. And a matter-antimatter drive, even at perfect efficiency, would still require the ship to carry fuel mass comparable to its payload mass for journeys of even moderate length, because the fuel itself must be accelerated along with everything else. These are engineering barriers. They are staggering. They may take centuries or millennia to overcome, if they can be overcome at all. But they occupy a fundamentally different category from the speed of light wall. Engineering barriers are finite. They involve specific materials, specific energy densities, specific manufacturing capabilities. They yield, historically, to sustained effort and accumulated knowledge. The speed of light wall does not yield. It is not made of materials. It is not limited by manufacturing. It is the shape of reality itself. And so the picture that emerges, the honest picture, grounded in confirmed physics, is one of constrained but genuine possibility. The universe permits interstellar travel. It even permits intergalactic travel, in principle. But it imposes a cost that is not measured in fuel or funding. The cost is temporal. Every journey at relativistic speeds is a one-way trip through time. You can cross the galaxy in a human lifetime, but you cannot return to the century you departed from. The universe will carry you across space, but it charges you in years, not your years, but everyone else's. This temporal cost reframes the Fermi paradox, the famous question of why, if intelligent life is common in the universe, we have not detected any evidence of it. The usual framing imagines alien civilizations building galactic empires, colonizing star systems, sending probes and signals across the cosmos. But the speed of light wall makes galactic empires effectively impossible to maintain. Communication between star systems requires years, decades, or centuries for a single exchange. A colony 20 light-years away cannot ask the homeworld for advice and receive an answer in less than 40 years. Political coordination across galactic distances requires thousands of years per decision cycle. No government, no economy, no social structure can function at that communication delay. Galactic civilizations, if they exist, must fragment into isolated pockets, each one evolving independently, each one separated from its neighbors, not merely by space, but by the relentless accumulation of time. Now imagine the most optimistic scenario, the one that Fermi paradox discussions rarely examine through the lens of light speed constraints. Suppose tomorrow, a radio telescope detects an unambiguous artificial signal from a star system 1,000 light-years away. The signal is structured, clearly technological, unmistakably the product of intelligence. Humanity confirms it. The discovery is announced. The world celebrates. We are not alone. Then the mathematics settles in. The signal we receive today was transmitted 1,000 years ago. The civilization that sent it existed during what we call the Middle Ages on Earth. We know nothing about them as they are now. They may have advanced beyond recognition. They may have destroyed themselves. They may have evolved into something we would not classify as intelligent by our standards. We have no way to know, because the information is a millennium old. We compose a reply. We transmit it at the speed of light, the fastest any message can travel. That reply will arrive at the source star in another 1,000 years. If the civilization still exists, if they still monitor the frequency, if they recognize our signal and compose a response, that response will take another 1,000 years to reach us. The full exchange spans 3,000 years, 1,000 for their signal to reach us, 1,000 for our reply to reach them, and 1,000 for their response to return. The humans who finally receive that response will be separated from the humans who first detected the alien signal by 100 generations. No living person will participate in both halves of the exchange. No institution, no language, no culture currently existing on Earth is likely to survive intact across that span. This is not a conversation. It is an archaeological correspondence. Messages exchanged between civilizations that share no living memory, no common culture, no mutual context. Each transmission is a time capsule launched into a future that neither sender can predict or inhabit. The speed of light does not merely slow communication with alien intelligence. It fragments it across timescales that exceed the lifespan of civilizations themselves. The silence of the cosmos may not indicate the absence of intelligence. It may indicate the presence of this wall. Civilizations may be abundant, thriving around millions of stars, but each one is imprisoned within its own light cone, the finite region of space-time from which signals can reach it. They can observe, they can send messages, but the universe is structured so that meaningful interaction across interstellar distances is agonizingly slow, and meaningful interaction across galactic distances is effectively impossible within the lifespan of any single civilization. This realization carries a weight that goes beyond physics. The speed of light is not merely a constraint on rockets and spacecraft. It is a constraint on knowledge, on connection, on the fundamental ability of conscious beings to reach out across the darkness and make contact with others who might share their questions. The universe is vast and possibly teeming with life, but it is structured so that each pocket of awareness develops in isolation, looking out at a sky full of stars it can see but cannot touch, listening for signals that may be centuries old by the time they arrive, sending replies that will not be received until the sender is long dead. There is a particular kind of loneliness encoded in these equations. Not the loneliness of being alone in the universe, which may or may not be our condition, but the loneliness of being separated from potential companions by a barrier that physics itself enforces. Even if the galaxy is rich with intelligent life, the speed of light ensures that each civilization's window of contact with any other is narrow, fragile, and mediated by the patience of generations. And yet, within these constraints, within this wall that cannot be breached, this temporal cost that cannot be avoided, this isolation that physics imposes, there is something worth noticing. The universe did not have to permit relativistic travel at all. The laws of physics could have been configured so that time dilation did not exist, so that energy costs rose even faster, so that the approach to light speed was not merely difficult, but immediately lethal at any appreciable fraction of c. In a slightly different universe, interstellar travel might be not just impractical, but genuinely impossible, forbidden by barriers far more severe than the ones we face. Instead, the universe we inhabit offers a narrow but real path. Accelerate at a comfortable 1G, and you can reach nearby stars within years. Push the journey to decades and you can cross the galaxy. Accept the temporal cost and the engineering challenge, and the observable universe itself. 93 billion light-years of galaxies, clusters, filaments, and voids becomes accessible within a single human lifetime of ship time. The wall at sea is absolute, but the space beneath that wall is vast, and the tools that space-time provides, time dilation, length contraction, the asymptotic approach to a limit that can never be reached but can always be approached more closely, are remarkably generous. The experimental confirmations of special relativity are not footnotes to this story. They are the story. Every GPS satellite correction, every muon reaching the ground from the upper atmosphere, every proton circling the LHC at 7,000 times its rest mass energy, every atomic clock that drifts by exactly the predicted number of nanoseconds. Each one is a data point, confirming that the universe behaves precisely as Einstein described. Time dilation is real, length contraction is real, the energy wall at sea is real, and the consequences of these facts for travel, for communication, for the possibility of contact between civilizations are not speculative. They follow directly from physics that has been measured to extraordinary precision over more than a century. The speed of light is often described as a speed limit, and the metaphor is understandable but subtly misleading. A speed limit is an external rule imposed on a system that could, in principle, operate without it. Remove the speed limit sign and the road still exists. The car still functions. You simply go faster. The speed of light is not like a speed limit sign posted on the road of space-time. It is more like the curvature of the Earth's surface. You cannot walk in a straight line on Earth's surface and end up farther from your starting point than half the planet's circumference, no matter how far you walk. This is not because walking is prohibited or because you lack energy. It is because the surface curves. The geometry constrains the outcome. The speed of light constrains motion through space-time, for the same reason the geometry of space-time is configured, so that massive objects trace paths that asymptotically approach C but never reach it. This is what actually happens if you try to reach the speed of light. Your clock slows down relative to the universe around you. The space ahead of you compresses. The energy required to push you faster rises toward infinity. The radiation environment ahead becomes lethal. The visible sky collapses into a single brilliant point of blue-shifted light, while darkness swallows everything behind. Your mass, your resistance to further acceleration climbs without limit. Every additional increment of velocity costs more than everything that preceded it combined. And the final, vanishingly thin gap between your velocity and C remains forever out of reach, separated from you by an energy deficit that exceeds the total contents of the observable universe. You cannot reach the speed of light. This is not a technological limitation. It is not a failure of ambition. It is a structural rule of the cosmos, written into the geometry of space-time at the most fundamental level physics has ever accessed. The wall is real, confirmed, and absolute. But here is the part that matters most. The wall does not mean the stars are beyond us. It means the stars require a different kind of courage than the one science fiction imagined, not the courage to break the laws of physics, but the courage to accept them. To accept that a journey across the galaxy means leaving behind everything and everyone you know. To accept that a signal sent to a distant civilization may not receive a reply for generations. To accept that the universe is built on a scale that dwarfs individual human lives, and yet permits those lives, if they are brave enough and patient enough, to cross distances that light itself requires millennia to span. The speed of light is the deepest boundary we know. It separates what is possible from what is not, what can be reached from what lies forever beyond reach, what can be known from what must remain unknown. It is not a prison wall. It is the architecture of the house we live in, immovable, unyielding, but enclosing a space so vast and so full of possibility that no civilization, no matter how advanced, could exhaust its contents in 1 trillion years. We live in a universe that bends time for travelers, compresses space for the bold, and opens pathways across the cosmos to anyone willing to pay the price in years. The wall at the speed of light is absolute. But the universe it defines is not small, it is not closed, it is not hostile, it is simply honest, offering the stars to anyone who accepts the terms, and asking in return only that we understand the rules of the house before we step through the door.